Welcome. My name is Viktor Terbrant. I work in Central Market Unit Petrochemical, Alfa Laval. This presentation is about how to turn your waste heat to profit. The International Energy Agency, IEA, predicts world demand of energy to increase by close to 50% over the next 20 years. At the time, oil reserves are declining, and the oil that is produced is harder to come by, being produced in more and more remote locations. Added to this comes tougher environmental legislation as carbon emission taxes are applied more widely. The combined effect is that the cost for buying and using energy will increase. McKinsey, the consultancy, has looked long and hard on different ways to secure an affordable energy supply while still controlling the environmental impact. Investments in energy efficiency were compared to investments in alternatives other than fossil fuels, such as nuclear, solar, wind and biofuels. McKinsey concluded that energy efficiency in process industry stands out as the single most attractive and affordable option. In fact, there is 3 times the world nuclear capacity of 2005 to be saved. If we take a closer look at the process industry as an energy consumer, we know that an average plant today consumes around 50% more energy compared to the most optimized plant. So there is no question that there is a large potential for improving energy efficiency in plants around the world. Heat exchangers and waste heat recovery play an important role to improve energy efficiency in the process industry. Waste heat recovery means applying heat exchanger to recover energy from process or utility streams and making use of the recovered energy to improve the net energy consumption in a plant. So it means to install heat transfer capacity to capture the energy before it is lost in the drains or to the atmosphere. This graph compares an interchanger or a preheater using shell and tubes or a compact heat exchanger. Plants often stop at 70% of heat recovery in preheaters or interchangers. Doing more is not profitable for shell and tubes, but compact heat exchangers can, to similar cost, achieve much more. This means that in many plants there is up to 36% more energy to be saved by just switching heat exchangers. And to those plants who consider to improve waste heat recovery, I strongly recommend to take compact heat exchangers into the equation. Why is this the case? I've met plant managers telling me that the plant is already energy efficient, and they sometimes even have a pinch analysis. Looking at this pinch analysis, it often becomes evident that it's based on shell and tube heat exchangers. A closer temperature approach is quite often possible with compact heat exchangers, resulting in less energy consumption and with good profitability. The next illustration shows the difference between outdated shell and tubes and up-to-date efficient waste heat recovery with compact heat exchangers. There are more cases where heat exchangers can actually improve the performance of a plant, direct or indirect, than one might think. Take a look at these boxes and see if you find anything of interest. Are you hungry? I give you 5 low-hanging fruits. Heat integration, one of the most direct ways to improve energy efficiency in the plant. Let the next animation illustrate how and why heat integration with compact heat exchangers is profitable. Alfa Laval made a study to make use of 10 megawatts of heat from a sulfuric acid plant and use it in a nearby plant, such as a copper or a zinc plant, resulting in reduced need from, for example, a coal-fired boiler. 2 cases were made, one where the plant was 200 meters away and one where the plant was 1,000 meters away, and the total system cost was included, such as heat exchangers, piping, instrumentation and civil works. This is the result based on the steam price. As you can see, even at moderate steam prices, it is a very profitable investment. In this kind of connected systems, people may be afraid of interdependence. Well, if the sulfuric acid plant stops, there is a backup steam heater installed, so the heat can be supplied anyway. And if the nearby plant shuts down, there is a trim cooler installed, so that the heat from the sulfuric acid plant can be cooled off anyway. All these backup units are accounted for in the study that Alfa Laval has made. Evaporation system revamping. This example shows a 600 ton per day caustic soda plant revamp going from 2 to 3 effects. The payback period is shown to the right. As you can see, even at moderate steam prices, the payback period is very attractive. In fact, going from 2 to 3 effects means a 30% reduction of steam consumption. Waste steam generation. Let's say we have a stream with hot flue gases, as the picture shows, that goes right out in the air. By installing a waste steam generator, it's quite possible to make use of a substantial amount of that heat. This steam can either be used direct in the plant or transformed into electricity. Here is the profitability calculation. Reduce heating utility temperature. This example shows the switch from a shell and tube reboiler using 180 degrees medium pressure steam to a compact heat exchanger reboiler that uses 138 degrees low pressure steam. Which is cheaper? The payback period is calculated on the price difference between the medium pressure steam and the low pressure steam. Reduced fouling. The next animation shows the self-cleaning effect of spiral heat exchangers. The current slide shows the visp-breaking process in the refinery. The self-cleaning feature of the spiral heat exchanger comes well in hand in this process. Hot visp-broken residue preheats atmospheric or vacuum residue before it enters the furnace. What happens if this heat exchanger fouls up? Well, instead of the heat exchanger doing the preheat, the furnace will have to do the preheat. The result of this is higher fuel consumption in the furnace. These graphs show the performance of fouling heat exchangers. It shows shell and tubes versus spiral heat exchangers. The graph to the left, the red line, shows a shell and tube heat exchanger which is cleaned once every 6 months. So the efficiency goes steadily down until it's cleaned, when it's up 100% again. The green graph shows a shell and tube heat exchanger that is cleaned every month, and the blue line shows a spiral heat exchanger with its self-cleaning effect. The graph to the right shows the payback period when replacing existing shell and tube with spiral heat exchanger. The red line corresponds to the red line to the left, and the green line corresponds to the green line to the left. To summarize, energy costs are high and everything points to an increase in the future. Heat exchangers play an important role in waste heat recovery, and compact heat exchangers add further opportunities for energy efficiency at very high profitability.